It's pretty incredible to think that our entire digital world, everything from your smartphone to the internet itself, can be traced back to a single paper written in 1948 by one guy, a mathematician named Claude Shannon. This one document literally laid the foundation for the age of information. So let's get into it and see what made this paper so revolutionary. At its very core, Shannon's work was all about answering one huge fundamental question. He was trying to figure out how we can send a message from point A to point B and have it arrive perfectly, or at least pretty darn close to perfect, when the universe is just filled with static and interference. So, to tackle this massive problem, Shannon did what any genius does. He broke it down. He created this elegant, universal model that could describe literally any communication system you can think of. And he boiled it all down to just 5 key parts. Okay, first up, it all starts with an information source. And that's really just whatever's creating the message. It could be a person talking, a computer spitting out data, or even the light coming from a scene being filmed by a TV camera. Next, that message has to go to a transmitter. Now, the transmitter has a super important job. It takes that message and encodes it, turns it into a signal that can actually be sent. Think of it like a modem, turning computer data into those screechy dial-up sounds we all used to know. And where does that signal travel? Through the channel, of course. This is the pipeline, right? It could be a copper wire, the airwaves for radio, a fiber optic cable carrying light. It's just the medium that gets the signal from here to there. On the other end of that channel, we have the receiver. Its job is basically the reverse of the transmitter. It has to catch that signal and decode it back into the original message. But, and this is a big but, the channel is where our villain enters the story, noise. This is where things can get messed up. And finally, if all goes well, that decoded message reaches its destination, the person or the machine it was meant for. And that's the whole chain. What's so amazing is that this simple diagram, it describes every communication system. It's the framework for everything he did next. With that model set, this is where things get really wild. Shannon realized that to solve the engineering problem, he had to do something totally radical. He had to completely separate the idea of information from the idea of meaning. Think about that for a second. To an engineer, Shannon said, the meaning is irrelevant. Information isn't about what you're saying, it's a measure of surprise. It's about how much uncertainty is removed when you pick one message out of all the possible messages you could have sent. The more choices you have, the more information is in your choice. And to measure this stuff, he needed a unit, a fundamental particle of information, if you will. He called it the bit, short for binary digit. 1 bit is the amount of information in a simple coin flip, a yes or no question. It's the absolute basic building block of it all. Okay, so if information is all about surprise, how do you actually put a number on it? Well, Shannon looked over at the field of thermodynamics and borrowed a really cool concept, entropy. In his world, higher entropy just means more surprise, more randomness, and therefore more information. To see what he meant, check this out. This is a mess of random letters, right? Every single character is a total surprise. You have absolutely no clue what's coming next. This is maximum entropy. It's packed with information because it's completely unpredictable. But of course, that's not how real language works. Now look at this string. It's still gibberish, but it feels a little more familiar. Why? Because the letters are following each other based on how common those pairs are in English. The randomness is going down, and so is the entropy. It's less surprising. And now we take it a step further. Here, we're not just looking at letter pairs, but the probability of entire words following each other. All of a sudden, it almost starts making sense, you see? The more structure and predictability we have, the less surprising it is and the lower the entropy. Shannon actually calculated that English is about 50% redundant. Half of what we write is kind of dictated by the rules of the language. All right, so we can measure information in bits. The next logical question for an engineer like Shannon was how fast can we push these bits down a perfect pipe, a channel with no noise at all? He gave this a name, channel capacity, or C. Think of it as the ultimate, unbreakable speed limit for information on any given highway. It's not a suggestion from an engineer, it's a fundamental law, like the speed of light. And this leads to his first huge theorem, and it's just beautiful in its simplicity. It says that you can have perfect, error-free communication as long as the rate you're sending information, your entropy, H, is less than or equal to the channel's speed limit, C. You're golden. But try to go even 1 bit per second over that limit? Nope. Impossible. But here's the catch. We don't live in a world of perfect noiseless pipes. In the real world, there's always a villain lurking in the channel, and that villain is noise. It's the random static that messes up our signal. So, let's say this is the clean signal we send out from our transmitter, a perfect, pristine string of ones and zeros representing our message. But on its journey, noise attacks it. And this is what arrives at the other end. You can see it, right? A couple of those bits got flipped. The third one went from a 1 to a 0. The message is wrong. It's been corrupted. So how do we measure that damage? Shannon had a word for it: equivocation. It's basically the receiver's confusion. After getting that messed up signal, how much uncertainty is left about what was actually sent? That remaining doubt, that's the information that noise stole from us. Now, up until this point, everyone, and I mean everyone in the field, thought that noise was an unbeatable foe. You could fight it, sure, you could shout louder, but you could never truly win. There would always be errors. Perfect communication in a noisy world was considered impossible. And then, Claude Shannon proved them all wrong. This right here is his masterpiece, the noisy channel coding theorem. And honestly, it's one of the most stunning, counterintuitive ideas in all of science. Shannon proved that as long as you stay under that channel speed limit C, you can achieve practically error-free communication. Not just a low error rate, but as close to 0 error as you want. How? By being clever, by adding smart, structured redundancy, what we now call error-correcting codes. You can literally beat random noise. Now here's the kicker. Shannon's paper was pure theory, pure mathematics. He proved these perfect codes must exist, but he didn't tell anyone how to actually build them. It took engineers and scientists decades to even get close to the limits he laid out. His theorem set the goal line, the absolute theoretical best we can do. And every single one of our modern communication systems, our Wi-Fi, our 5G, our probes in deep space, they're all still striving to reach that perfect limit that Shannon described all those years ago.